Deep in the cosmic night, where silence stretches for billions of light years and stars burn like distant embers, a colossal event is unfolding. Two spiral giants, galaxies each containing hundreds of billions of stars, are drifting toward one another on an inevitable collision course. We might imagine this as a catastrophic smash, like two planets shattering on impact, but galaxies are not solid objects. They are vast swarms of stars, nebulae, black holes, and invisible dark matter clouds. When galaxies collide, the outcome is stranger, more beautiful, and more profound than destruction. It is creation, transformation, and rebirth on the grandest scale imaginable. But what truly happens when galaxies merge? Do stars crash into one another? Do planets burn in stellar infernos? Or could collisions like these be responsible for the very conditions that allow civilizations like ours to exist? Tonight, we journey across deep time and deeper space to unravel the mysteries of galactic collision. We will uncover the signs written in the stars, explore the role of gravity as a cosmic sculptor, and confront the astonishing truth that our own Milky Way is destined to collide with the Andromeda Galaxy in the far future. This is not just an astronomical curiosity, it is our fate. Prepare yourself. We begin. Every galaxy in the universe is moving. Some drift gently in relative isolation. Others swirl in crowded neighborhoods, caught in gravitational embraces with their companion. The universe itself is expanding, driving galaxies away from one another across the vast void. Yet locally, gravity often wins. When galaxies are close enough, their mutual attraction pulls them together. Over millions, sometimes billions, of years, these giants drift into an intricate ballet choreographed by gravity. The result is not an instantaneous smash, but a slow-motion dance, unfolding over timescales so immense they are almost incomprehensible. From a cosmic perspective, galaxies glide like ghostly ships through an endless ocean, drawn inexorably into contact. Their spiral arms stretch, warp and twist, pulled into vast tidal streams that can span hundreds of thousands of light years. Gas clouds are ripped apart, compressed, and set ablaze with furious star formation. Black holes at galactic centers awaken, devouring matter and blazing with energy. The outcome is transformation, two galaxies merging into one entirely new entity. This is not speculation. We can see it happening right now. The night sky is full of examples of galactic collisions, frozen in different stages of their cosmic evolution. Look at the Antennae galaxies, 60 million light-years away in the constellation Corvus. Once two ordinary spirals, they are now entangled, their stars and dust flung outward in long, delicate streams that resemble insect antennae. In the constellation Canes Venatici, the Whirlpool Galaxy, M51 tugs at a smaller companion, distorting its arms into vast, curling tendrils. The Tadpole Galaxy, caught mid-collision, trails a spectacular ribbon of stars stretching 280,000 light-years into space. Each of these objects is a snapshot in a cosmic story that plays out over eons. Through them, astronomers piece together the sequence of events that occurs when galaxies collide, a sequence that will one day rewrite the night sky for Earth's distant descendant. The question many first ask is simple. When two galaxies collide, do their stars slam into each other like billiard balls? The answer is both surprising and counterintuitive. Despite the immense number of stars, billions upon billions, galaxies are mostly empty space. Imagine two swarms of bees colliding in the sky. Most bees will pass right by one another without touching. So it is with stars. The distances between them are so vast that direct collisions are exceedingly rare. But this does not mean collisions are uneventful. Gravity's invisible hand reshapes everything. Stars are slingshotted onto new orbits. Some are flung into deep space, cast adrift as rogue stars wandering the void between galaxies. Others are pulled inward toward galactic centers, spiraling closer to the supermassive black holes that lurk there. While stars rarely crash, entire planetary systems can be destabilized. Planets might be ripped from their suns, condemned to drift eternally in the cold of interstellar space. Others might be hurled into fiery deaths as their orbits decay. For life clinging to fragile worlds, a galactic collision is not gentle, it is chaos. And yet from this chaos comes brilliance. Galactic collisions are engines of creation. When two galaxies interpenetrate, their vast clouds of hydrogen gas are squeezed and compressed. Shock waves ripple through interstellar space, igniting furious waves of star formation. New stars blaze into existence by the millions, creating dazzling starburst galaxies, cosmic fireworks, visible across the universe. Some of the brightest galaxies ever observed owe their radiance to these bursts of starbirth, triggered by galactic mergers. The light we see from colliding galaxies is not only destruction, it is a beacon of rebirth. Where gas once drifted silently through space, now clusters of brilliant young stars shine, some destined to host planets, and perhaps in unimaginable futures, new life. And yet from this chaos comes brilliance. Galactic collisions are engines of creation. When two galaxies interpenetrate, their vast clouds of hydrogen gas are squeezed and compressed. Shock waves ripple through interstellar space, igniting furious waves of star formation. New stars blaze into existence by the millions, creating dazzling starburst galaxies, cosmic fireworks, visible across the universe. Some of the brightest galaxies ever observed owe their radiance to these bursts of starbirth, triggered by galactic merger. The light we see from colliding galaxies is not only destruction, it is a beacon of rebirth. Where gas once drifted silently through space, now clusters of brilliant young stars shine, some destined to host planets, and perhaps in unimaginable futures, new life. This is not a distant curiosity. The Milky Way itself is on a collision course. In roughly 4.5 billion years, our galaxy will meet Andromeda. The two are already rushing toward one another at 11. When they collide, their stars will dance, their gas clouds will ignite with new starbirth, and their central black holes will merge. The night sky above Earth, or whatever worlds exist then, will blaze with unfamiliar splendor. The graceful spiral of Andromeda will grow, fill the heavens, and finally entangle with the Milky Way in a cosmic embrace. The result will be a new galaxy, sometimes called Milkymeda. Its stars will include our Sun, still burning, though nearing the end of its life. Humanity may be long gone, but the legacy of our galaxy will continue in this grand merger. This is the beginning of our story, a tale of gravity, chaos, and creation. But the mysteries deepen. If galactic collisions are so common, what role have they played in shaping the universe we see today? Could the very conditions for life owe their existence to cosmic violence on unimaginable scales? And is it possible that civilizations before us once watched their skies transformed by the same events that await us? The answers lie in the evidence scattered across the cosmos. And in the next chapter, we will venture deeper into that evidence, unraveling how astronomers detect and decode these colossal encounters, and what the earliest galactic collisions may tell us about the birth of structure in the universe. The story of colliding galaxies is written not only in spectacular images, but also in faint whispers of light and energy that reach us across unimaginable distances. Astronomers have learned to read these messages, decoding the stages of galactic encounters the way paleontologists read fossils. Each collision leaves behind scars and signatures, distorted spiral arms, long tidal tails, compact starburst regions, and the sudden awakening of once quiet black holes. To understand what happens when two galaxies collide, we must become detectives of light, piecing together the evidence scattered across the cosmos. The first clue comes from the shapes of galaxies themselves. Many appear warped, twisted, or strangely elongated. Spirals are stretched into ellipses, barred into strange asymmetries, or pulled into delicate bridges of stars. These structures are not random. They are gravitational tides on scales larger than anything we can easily imagine. Just as the moon raises tides on Earth's oceans, a passing galaxy raises tides on another's stars and gas. When galaxies draw close, their gravity drags out great streams of material. Sometimes these streams extend for hundreds of thousands of light years, shining faintly as trails of scattered suns. These stellar tides are the fingerprints of collision, but light alone is not enough. Modern telescopes peer deeper, across multiple wavelengths, to reveal what the human eye cannot. Radio telescopes detect the faint emission of cold hydrogen gas being stretched and compressed. Infrared observatories expose newborn stars hidden in dusty nurseries, their light invisible to optical instruments. X-ray telescopes capture the furious glow of gas heated to millions of degrees, as black holes awaken and supernovae erupt. Each wavelength adds a layer of understanding, like different instruments in a cosmic orchestra, revealing the full power of the galactic symphony. Perhaps the most telling evidence comes from computer simulation. Using the laws of physics and the raw data of observed galaxies, astronomers can recreate the slow-motion dance of collisions across billions of years. In these virtual universes, two spirals approach, intertwine, and merge into a single remnant. The simulations match perfectly the structures we see in the sky: tails, bridges, shells, and bursts of star formation. What once seemed chaotic becomes predictable. The universe, in its grandeur, obeys rules as consistent as they are vast. The dance of galaxies, though slow, is choreographed with precision. Yet every simulation also carries a haunting reminder. Collisions are not rare, they are essential. Without them, galaxies would remain small and dim, star formation would falter, and the universe would look far different than it does today. Collisions are not accidents, they are the very engines of cosmic evolution. The Milky Way itself is the product of countless mergers, having swallowed smaller galaxies throughout its history. Every star in our night sky may once have belonged to another, long-forgotten galaxy, now absorbed into our own, and the evidence of these ancient feasts remain. Astronomers detect faint streams of stars looping around the Milky Way, remnants of dwarf galaxies devoured long ago. Our halo is littered with these ghostly arcs, each the trace of a smaller galaxy torn apart by gravity. The Sagittarius dwarf galaxy, currently in the process of being consumed, provides a living example of how galaxies grow by cannibalizing one another. The great spiral we call home is not a static island of stars, but a creature still feeding, still changing, shaped by collision after collision. But if collisions are so vital, what did the earliest ones look like? To answer this, astronomers look back in time, because light travels at a finite speed. Every telescope is also a time machine. Distant galaxies show us the universe, as it was billions of years ago. And what do we see in that young universe? A chaotic cosmos, where collisions were far more common. Small proto-galaxies crashed together constantly, building ever larger structures. The smooth spirals we admire today are the result of billions of years of such merging. Without them, no grand galaxies would exist, and without galaxies, stars like our Sun and planets like Earth might never have formed. In this light, galactic collisions are not catastrophes, but acts of creation. They forge the environments where heavy elements are produced and spread, where gas clouds collapse into stars, and where planetary systems are born. The calcium in our bones, the iron in our blood, the oxygen we breathe, all owe their existence to generations of stars, many of which were sparked into life by collisions between galaxies. The violence of gravity is the sculptor of everything we know. Yet there is another layer to this story, one that ventures beyond astronomy into speculation. If collisions are so fundamental to the creation of stars and planets, then they may also be fundamental to the emergence of life. Civilizations like ours might exist precisely because galaxies collide. If the cosmos were a quieter place, with galaxies drifting forever apart, perhaps the raw ingredients of biology would remain locked in primordial gas, never igniting into stars, never condensing into worlds. The very fact that we can ask these questions might be the product of countless galactic mergers before us. Still, there is a paradox. While collisions can spark creation, they can also destabilize the delicate balance required for life. A planetary system flung from its star has no hope of survival. A world roasted by supernova radiation may never recover. Civilization itself could be vulnerable to the upheaval of a galactic merger. The same events that give rise to life may also set the stage for its destruction. The line between creation and annihilation is razor thin, and gravity does not care which side of that line we fall on. This duality, cosmic destruction, intertwined with cosmic creation, is at the heart of the story. Galactic collisions are not good or bad, not kind or cruel. They are inevitable. They are the universe shaping itself on scales that dwarf human comprehension. And the more we study them, the more we realize how deeply our own existence is tied to these distant, slow-motion encounters. But questions remain. If collisions are so common, why is the night sky above us still so serene? Where are the scars in our own galaxy? How long before the serenity ends, and the great transformation begins. To find the answers, we must follow the evidence deeper, into the hidden structure of the Milky Way and its looming encounter with Andromeda. The evidence is there, written in the motions of stars, in the pull of dark matter, and in the faint glow of galaxies already colliding in the distance. The mystery is far from over. It is only beginning. The evidence that our own galaxy is destined for collision is already all around us, written in the motions of stars and the pull of gravity that stretches across millions of light years. For centuries, Andromeda has been a faint smudge in our northern skies, visible even without a telescope as a pale blur. To the naked eye it seems eternal and unmoving, but in reality, it is rushing toward us at breathtaking speed. Modern instruments, capable of measuring the tiniest shifts in light, reveal the truth. Andromeda and the Milky Way are locked in a gravitational embrace, closing the gap between them at over 110 kilometers every second. Though the distances are staggering, the outcome is inevitable. Our galaxies are destined to merge, and the countdown has already begun. For a long time, scientists debated whether Andromeda was truly approaching us, or merely drifting sideways. Its vast distance made its motion nearly impossible to detect with the naked eye. Only with the precision of space telescopes did the story become clear. The light of Andromeda is shifted slightly toward the blue end of the spectrum, a sign that it is moving closer, not farther away. Additional measurements from the Hubble Space Telescope confirmed its sideways motion is too small to prevent a collision. The verdict is in. In roughly 4.5 billion years, the Milky Way and Andromeda will meet head-on. This is not speculation. It is a scheduled event in the future history of our cosmos. The idea of such a colossal event can feel abstract, almost ungraspable. But astronomers have gone further than prediction. They have run detailed simulations, plugging in everything we know about the two galaxies: their mass, their dark matter halos, the orbits of their stars, the distribution of their gas. What emerges from these simulations is breathtaking. Over the course of several billion years, Andromeda will loom larger and larger in our skies. Its spiral arms will stretch across the heavens, outshining every star and constellation we know today. The serene dome of night will become a dynamic canvas of galactic light, shifting over millennia in slow but unstoppable transformation. The first encounter will not be a violent crash. The two galaxies will pass through one another, their stars largely untouched, but their shapes shredded by gravitational tides. Spiral arms will warp, twist, and fling out long streams of stars. New clusters will ignite as their gas clouds compress and collapse. The galaxies will swing past, then reverse under the pull of gravity, colliding again and again like dancers crossing a floor before embracing fully. Over several passes, their structures will dissolve, until finally the two spirals merge into a single massive elliptical galaxy. Astronomers have already given it a name: Milkomeda, a cosmic child born of two giants. But what does this mean for our Sun, for Earth, and for whatever descendants may exist by then? Simulations suggest that the Sun will likely survive the collision intact, drifting into a new orbit around the center of the merged galaxy. Stars are simply too far apart to collide directly. However, the Sun's position in the galaxy may change dramatically. It could be flung outward into a long tidal tail, carrying its planets into the dark outskirts. Or it could be pulled inward, closer to the new galactic core, where radiation and chaos may reign. Either fate would transform the cosmic environment of our solar system forever. For Earth itself, time will already be short. By then, the Sun will be nearing the end of its stable life, swelling into a red giant. The collision will be less a threat than a backdrop to the final chapter of our planet's story. The collision, however, will not end with chaos alone. It will be a spark of new beginnings. When the gas clouds of the Milky Way and Andromeda slam together, they will ignite titanic waves of star formation. For billions of years afterward, the merged galaxy will blaze with new suns, many surrounded by planets. Though Earth may be gone, other worlds may rise, perhaps bearing their own forms of life, nurtured by the very collision that ended one chapter of cosmic history. In this sense, our destiny is not an ending but a handoff, passing the torch of life to other stars born from the fires of collision. Even now, astronomers search for echoes of future events by studying other galaxies already in the throes of merging. They are cosmic previews of what awaits us. The Whirlpool Galaxy reveals the first stages of gravitational entanglement. The Antennae galaxies show the next act, with their long tidal tails stretching like glowing wings across the void. The final act can be seen in giant elliptical galaxies, once spirals like ours, now smoothed into vast, featureless orbs of stars. These remnants are the afterimages of collisions long past, cosmic tombstones and birthplaces in one. But the fate of the Milky Way and Andromeda may not be limited to themselves alone. Nearby lies the Triangulum Galaxy, smaller but still substantial. Its gravitational pull hints that it may join the collision, either as a spectator orbiting the merger, or as a participant drawn into the chaos. If so, Milkomeda may not be a child of two but of three, a vast galactic family converging into a single future. The local group, our galactic neighborhood, may eventually collapse into one super galaxy, a glowing beacon adrift in an expanding universe. When we think of collisions, we imagine destruction, cars crumple, planets shatter, asteroids blast craters into worlds. But galaxies collide different. They do not smash so much as interweave. They merge not in violence, but in transformation. And through this process they build the structures of the universe we inhabit. Without collisions, there would be no great galaxies, no endless streams of stars, perhaps no life. Our own existence is the legacy of a billion years of galactic encounters. And soon, in cosmic terms, we will witness our own galaxy's turn to dance. The question that lingers is whether such a colossal event, though inevitable, carries lessons for us now. Do civilizations elsewhere in the cosmos survive their galactic collisions? Do they adapt, migrating to safer stars, as their home systems are flung into peril? Or do many vanish, erased not by war or famine, but by the grand mechanics of gravity? The silence of the universe may hide an answer. Perhaps life is common, but the stability required for civilizations to thrive is fragile, always threatened by the slow but unstoppable drift of galaxies toward one another. Our story may be just one, in an endless cycle of creation and erasure, written across the stars. The Milky Way and Andromeda's collision is not an ending but a beginning, yet beginnings and endings are always intertwined. The stars will endure, the galaxies will merge, life may rise again, and the universe will continue its endless dance of destruction and creation, forever sculpted by the invisible hand of gravity. When we imagine the future collision of the Milky Way and Andromeda, we often picture a single moment of impact, as if two colossal objects were slamming together in a shattering crash. But the truth is far stranger. A galactic collision is not a single instant, but a drawn-out performance, a cosmic play that unfolds over billions of years. To an observer watching in real time, it would seem almost motionless. Stars would drift across the heavens with only the faintest of changes visible within a human lifetime. Yet stretch those years into the long view of cosmic history, and the slow choreography reveals itself as one of the most magnificent transformations the universe has to offer. The first act of this drama begins long before the galaxies physically meet. Their halos of dark matter, the invisible scaffolding that surrounds every galaxy, intermingle first. Dark matter does not shine, but it makes up most of the mass of each galaxy. These halos extend for hundreds of thousands of light years, overlapping and tugging at each other's stars before the spirals themselves come close. Already, the gravitational embrace is beginning. The galaxies are bound, and the path of their future is. As they draw nearer, the stars along their outer arms feel the pull. Some are ejected entirely, cast loose into the intergalactic medium as wandering exiles. These are the rogue stars, lone travelers that may drift forever between galaxies, never to find another home. Others are flung into elongated orbits, tracing vast loops that carry them thousands of light years from their origins before they fall back again. The galaxies themselves begin to distort. Their elegant spirals warp. Their disks ripple like waves on an ocean. To look upon them at this stage is to see familiar shapes stretched into strange and ghostly forms. When the galactic disks finally overlap, something dramatic happens, not to the stars, which mostly pass by untouched, but to the gas that fills the space between them. Unlike stars, gas clouds cannot simply slip through one another. They collide head-on, compressing into dense shock fronts that trigger rapid star formation. These newborn stars, blue and massive, blaze fiercely and live briefly. They end their lives in brilliant supernovae, seeding the surrounding space with heavy elements. In these few 100 million years, More stars may form than in the several billion years of quiescence that preceded the encounter. The galaxies, once serene, now erupt with stellar fireworks. At the same time, the great engines at the hearts of both galaxies awaken, each supermassive black hole, fed by a torrent of new material funneled inward by gravitational chaos, ignites as a quasar. For a time, the centers of the merging galaxies shine brighter than all their stars combined. Jets of radiation stream outward, piercing the darkness across millions of light years. These are among the most violent beacons in the cosmos, and they are born in the chaos of collision. But the dance does not end here. After their first pass, the galaxies continue on their courses, stretched and battered but still distinct. Gravity slows them, pulls them back together, and they collide again. Each encounter strips away more of their individuality. Spirals become unrecognizable. Their graceful arms dissolve into ragged streams of stars that weave around the merging pair like ribbons. Over time, repeated passes bring them closer and closer, until at last the two galaxies settle into one. The process takes billions of years, far longer than the span of human history, but on cosmic scales it is a fleeting moment. The end result is a new kind of galaxy altogether. The neat spiral structures vanish, replaced by an enormous elliptical galaxy, smooth and swollen with stars. Its core burns with the remnants of furious starbirth. Its halo is littered with the trails of stars cast off during the merger. The central black holes, after spiraling together for eons, finally merge into one, even greater singularity. The new galaxy, vast and glowing, carries within it the history of both its parents. Every star, every cluster, every fragment of gas now part of a larger whole. To those who might one day look upon the sky from within such a merged galaxy, the transformation would be extraordinary. Where once the night was filled with the familiar band of the Milky Way, now the heavens blaze with countless new stars, scattered across a sky that changes visibly over the ages. Familiar constellations would vanish as stars shift positions, replaced by patterns never seen before. The collision would not simply reshape the galaxy, it would redefine the very canvas on which civilizations look upward to seek meaning in the stars. It is tempting to view this story as violent, even apocalyptic, but the truth is more subtle. Galactic collisions are less about destruction than they are about transformation. Stars are not shattered, but reborn into new configurations. Gas is not lost, but ignited into new generations of suns. Black holes do not end creation, but redistribute it, shaping galaxies with their power. The process is chaotic and beautiful, filled with loss and creation, endings and beginnings intertwined so deeply they cannot be separated. And perhaps most astonishing of all is the realization that this story is not unusual. Across the cosmos, galactic collisions are common. Nearly every large galaxy has undergone them, and many are in the process of merging right now. The universe is filled with these slow, stately dances, each one unique yet governed by the same relentless laws of gravity. Our own impending collision with Andromeda is not a special exception. It is the natural fate of galaxies, the way the universe builds its grandest structures. What we see as catastrophic is, in truth, the engine of creation. And as we gaze into the depths of space, watching other galaxies collide, we are also gazing into our own future. What happens when two galaxies collide is not an abstract question. It is a chapter waiting to be written in the history of our own sky, a destiny already unfolding, slow and inevitable, under the guiding hand of gravity. The galaxies that collide are more than collections of stars and glowing nebulae. They are vast ecosystems bound together by forces we cannot see directly, but whose influence shapes every detail of the encounter. At the heart of this hidden framework is dark matter, the invisible substance that outweighs all the visible stars and gas by a factor of 5. Without it, galaxies would fly apart, unable to hold their spirals together. When galaxies collide, it is their dark matter halos that meet first, long before the luminous disks touch. These halos pass through each other like ghosts, but in doing so, they lock the galaxies into orbits that draw them together again and again until the final merger is complete. We know dark matter exists, not because we can see it, but because of the way it bends the universe. Stars at the edges of galaxies orbit too quickly to be held in place by visible matter alone. Only an unseen mass spread in a vast halo can account for their motion. In collisions, these halos dominate the dance. They stretch across hundreds of thousands of light years, overlapping, merging, and tugging the galaxies like invisible puppet strings. The stars respond to this pull, their orbits twisted into new shapes, their fates rewritten by forces that cannot be touched or observed directly. It is a reminder that the most important actors in the story of galactic collisions are not the blazing suns or the radiant gas clouds, but the invisible skeleton of the cosmos itself. In some collisions, we see the consequences of dark matter's presence etched clearly in light. When two clusters of galaxies, each containing hundreds of members, collided in a titanic encounter, astronomers observed something remarkable. The hot gas between the galaxies was slowed and shocked, emitting X-rays as it collided. But the galaxies themselves, and the invisible halos around them, passed through largely unhindered. Using gravitational lensing, scientists mapped the mass of the system and found that most of it had sailed ahead of the gas, separating cleanly from the visible matter. This system, known as the bullet cluster, became a striking piece of evidence that dark matter is real, and it also became a window into the role that dark matter plays in shaping every galactic encounter. If stars rarely collide in galactic mergers, gas behaves differently. Unlike stars, gas cannot simply pass through. When the gas clouds of two galaxies slam into one another, they are shocked and compressed. It is this process that ignites furious bursts of star formation, creating some of the brightest regions in the universe. In these regions, stars are born by the millions, often in dense clusters that outshine entire galaxies. These bursts can be so intense that they deplete the available gas within only a few 100 million years, burning through the raw material of creation like a wildfire. What remains afterward is a galaxy bright but exhausted, with little fuel left for future generations of stars. The collision both creates and consumes, giving rise to new brilliance while setting limits on what comes next. The role of gas in collisions does not stop with starburst. It also fuels the awakening of the supermassive black holes at galactic centers. Ordinarily, these black holes are quiet, feeding slowly and shining dimly, but the tidal forces of collisions drive rivers of gas inward, straight toward the central engine. As this gas spirals into the black hole, it heats to incredible temperatures, releasing torrents of radiation across the electromagnetic spectrum. For a brief cosmic moment, the galaxy becomes a quasar, a lighthouse of energy visible from billions of light years away. These quasars were most common in the young universe, when collisions were frequent and galaxies were rich in gas. By studying them, astronomers see not only the violence of mergers, but the fingerprints of how galaxies grew and evolved in the earliest time. The fate of black holes in collisions is a story unto itself. Each galaxy carries its own central black hole, millions or billions of times the mass of the Sun. As galaxies merge, these black holes spiral toward one another, their orbits shrinking as they lose energy to surrounding stars and gas. Eventually, they come close enough that the fabric of space-time itself begins to carry away their energy in the form of gravitational waves. In their final moments, as they merge into one, they release more power than all the stars in the universe combined, though for only an instant. These waves ripple outward across the cosmos, faint but unmistakable, carrying with them the echo of the galaxies that birthed them. The detection of such waves is more than a triumph of physics. It is a way of listening to the heartbeat of cosmic collisions themselves. These processes, dark matter shaping the encounter, gas igniting new stars, black holes blazing to life, make each collision a transformation rather than a mere crash. They turn galaxies from quiet spirals into luminous starburst factories, from serene disks into turbulent quasars. The remnants of these encounters, the great elliptical galaxies we see today, are the tombstones of these events, but also their children. They are not simple piles of stars, but the products of countless hidden processes, working together. The invisible pull of dark matter, the violent compression of gas, the inexorable hunger of black holes. Every elliptical galaxy in the sky is a frozen story of creation through destruction. And so when we ask what happens when galaxies collide, the answer is not simple. Stars dance to new orbits, gas clouds ignite into new suns, black holes awaken, merge and roar. Dark matter silently shapes the outcome, unseen but indispensable. Collisions are not accidents, they are the engines of cosmic history, the crucibles in which galaxies are transformed, and the seeds of future stars and worlds are sown. Without them, the universe, as we know it, would not exist. And within them lies the destiny of our own galaxy, waiting quietly across the ages, inevitable and unstoppable. When galaxies collide, the spectacle is usually described on the grandest scales. Tidal tails stretching for hundreds of thousands of light-years, quasars blazing at their centers, dark matter halos merging invisibly in the background. But hidden within these colossal events are the smaller, more intimate stories of individual stars and their planetary systems. For a civilization bound to a single world, it is not the fate of galaxies in the abstract that matters, but what happens to suns like our own, and the fragile worlds that orbit them. In the slow violence of a galactic collision, the stage of cosmic grandeur is also the theater of personal annihilation and unlikely survival. Though stars themselves rarely collide, the gravitational chaos of a merger is enough to transform their fate. Every star orbits within the gravity well of its galaxy, moving along paths that seem stable for billions of years. But when another galaxy arrives, its mass disrupts those delicate orbits. Some stars are pulled inward, plunging toward the galactic core. Others are accelerated outward, ejected into the intergalactic dark as rogue stars. This process is not gentle. Whole stellar neighborhoods are torn apart, star clusters unbound, and planetary systems left at the mercy of forces far larger than themselves. What was once a safe orbit can suddenly become a trajectory into exile. Planets too feel this upheaval. While the stars they orbit may remain intact, the overall stability of their systems can be threatened. A small gravitational nudge from a passing star, an encounter still rare, but far more likely during the crowded chaos of a merger, can disrupt the delicate balance of a planetary system. A planet may be hurled into interstellar space, cast away from its sun into eternal night. Others may be driven inward toward their stars, roasting in unbearable heat, or flung outward to freeze in distant orbits. For life clinging to such worlds, a galactic collision is not a distant astronomical curiosity. It is extinction written across the sky. Yet collisions do not always mean doom. In many cases, planetary systems remain surprisingly stable. Stars that are not drawn too close to the galactic core, or flung outward, may pass through the encounter relatively unscathed, carrying their planets with them into the new galaxy that emerges. A world that survives could one day look up into a sky transformed beyond recognition. Imagine standing on a habitable planet in such a system. The night sky would no longer show the familiar band of the Milky Way. Instead, it would blaze with the spirals of Andromeda, stretched across the heavens, growing larger with every passing millennium, until the two galaxies interweave. Constellations would dissolve, replaced by shifting patterns of stars scattered in tidal streams. It would be a view both terrifying and beautiful, a cosmic reminder of the fragility of existence. Among the most fascinating possibilities are the rogue planets, created in these upheavals, cast away from their suns, drifting through the void. These worlds seem inhospitable at first glance, yet some may harbor oceans beneath icy shells, warmed by internal heat long after their parent stars are gone. In a galaxy shaken by collision, such planets could become the last refuges of life, hidden worlds adrift in the dark. Others might be captured by new stars, beginning new histories in alien systems. Collisions do not only destroy, they shuffle the deck of creation, redistributing stars and planets in ways that may seem chaotic, but also open possibilities for life to take root in unexpected places. Civilizations, if they exist elsewhere in the cosmos, must face these realities. The slow time scale of a galactic collision means that intelligent beings would see its approach across countless generations. They would know that their galaxy is being drawn into another, that the future sky will transform, and that their star itself may one day be thrown into exile. The choices they make in response could determine whether they endure or vanish. Do they abandon their world for safer stars? Do they attempt to migrate across the changing galaxy? Or do they accept that survival on cosmic timescales is an illusion, and fade into history as their galaxy itself changes form? These are not merely scientific questions. They are questions of destiny, the kind that every civilization must face when confronted by the larger forces of the universe. Our own place in this story is not exempt. In 4.5 billion years, when the Milky Way and Andromeda collide, the Sun will still exist, though nearing its red giant phase. Earth may already be uninhabitable, its oceans boiled away by the swelling star. But the solar system as a whole will be swept into the merger, its fate determined by chance and gravity. Perhaps the Sun will drift calmly into the new galaxy's outskirts, its planets still orbiting in quiet obscurity. Perhaps it will be pulled toward the center, its worlds bathed in the radiation of a blazing quasar. Or perhaps it will be hurled into exile, a solitary traveler in the intergalactic dark. The destiny of our solar system is not written in detail, but its role in the larger cosmic drama is assured. When we look up at the stars, we see constancy. Constellations return with the seasons. The Milky Way arches across the sky as it has for all of human history. Yet this stability is an illusion born of short timescales. On the canvas of billions of years, the sky is restless. Stars drift, galaxies approach, and whole systems are torn apart and remade. Galactic collisions remind us that permanence is a fragile illusion. The universe is always in motion, always reshaping itself. And within that motion lies the story not only of galaxies and stars, but of the small, fragile worlds that orbit them. Perhaps this is the most humbling lesson of all. Collisions on cosmic scales are indifferent to the lives of individuals, species, or civilization. Yet without them, the universe would not have the complexity that allows life to exist in the first place. The same forces that may one day exile our sun also gave birth to it. The same gravitational tides that may scatter planets into the void also created the heavy elements that make planets possible. Destruction and creation are not separate forces. They are the same process, viewed from different perspectives, repeating endlessly across the universe. And in that cycle, our fragile worlds find both their peril and their possibility. The merged galaxy that will one day form, from the union of the Milky Way and Andromeda, will not simply be a larger version of what we see now. Its structure, its destiny, and even its relationship to the rest of the cosmos will be profoundly different. The elegant spiral arms that define our current galactic home will be in their place will rise a vast elliptical galaxy, smooth, swollen and luminous, its stars spread in a spheroidal halo that stretches far into space. Astronomers who study such galaxies elsewhere already know what the outcome will be. Milkomeda, as some call it, will be a giant, perhaps one of the brightest galaxies in our local group, a monument to the collision of two giants. But this monument will not last forever. The elliptical galaxy that emerges from the merger will be alive with star formation at first, fueled by the violent compression of gas during the collision. New stars will blaze into existence, by the millions, briefly flooding the galaxy with light. Yet this frenzy of creation will consume the available gas quickly. Elliptical galaxies are known for being red and dead, dominated by older stars with little raw material left for new generations. Once the burst of star birth fades, Milkomeda will begin to quiet. Its stars will age, redden, and die. What was once a thriving spiral will become a sedate giant, slowly fading into the cosmic dark. The timescales of this fading are difficult to grasp. Billions of years after the merger, the bright young stars will vanish, leaving behind long-lived dwarfs that burn dimly for trillions of years. In that distant future, Milkomeda will glow faintly, not with the brilliance of clustered suns, but with the combined light of countless small enduring embers. Civilizations, if they endure, will live under skies filled, not with the sparkling richness of diverse stellar populations, but with the quiet red light of ancient stars, spread evenly across the heavens. The age of galactic fireworks will be long past, replaced by an age of twilight. The role of dark matter in this future cannot be ignored. The newly formed galaxy will carry within it an immense halo of unseen matter, binding its stars and shaping its evolution. Without dark matter, the orbits of stars would decay, the structure of the galaxy would unravel, and the luminous remnant of the merger would dissolve into space. Instead, the halo will hold Milkomeda together for as long as the universe permits, preserving its identity even as its stars age and fade. The galaxy will remain coherent, a single, bound object, drifting in the void, long after its brilliance has dimmed. Yet the cosmic stage on which Milkomeda will exist is itself changing. The expansion of the universe is accelerating, driven by the mysterious force we call dark energy. Distant galaxies are receding from us at ever greater speeds, and in time, only those bound within our local group will remain visible. Billions of years after the collision, Milkomeda will be the only galaxy left in sight. All others will have disappeared beyond the cosmic horizon, carried away by expansion faster than light can bring their signals to us. For any future astronomers living within Milkomeda, the universe will appear empty. They will see only their own galaxy, isolated in an endless dark, and they may never know that other galaxies ever existed. This isolation carries profound implications. Our knowledge of the cosmos is possible only because we exist, at a moment when galaxies are still visible across vast distances. We can trace the history of the universe, measure its expansion, and understand its evolution, because light from billions of years ago still reaches us. In the far future, that light will no longer arrive. The universe's story will be hidden. Civilizations born in that age of cosmic solitude may look up and see only a single galaxy, believing themselves to be alone in a featureless void. Their science, no matter how advanced, will be constrained by what they can observe. In this sense, we live in a privileged moment, one that reveals truths that will one day be invisible. The transformation of the night sky during and after the merger would be staggering for any beings who witness it. Imagine the slow growth of Andromeda, swelling larger every 1,000 years, until it spans the heavens. Imagine the moment when its spiral arms stretch overhead, mingling with the familiar band of the Milky Way. Imagine the centuries of chaos as constellations shift, vanish, and reform into patterns unrecognizable to us now. And then, after the merger, imagine a sky filled with a smooth, glowing haze, brighter than anything we see today, stretching across the night as a reminder of the collision that birthed it. This will not be a single spectacle, but a transformation written across millions of years, visible to any who endure to watch. On the scales of stars and planets, the consequences are uncertain, but on the galactic scale, the story is clear. The collision will create something new, something that carries within it the memory of two galaxies, yet is itself entirely different. The Milky Way and Andromeda, names that anchor us to the night sky, will vanish. Their identities will dissolve into Milkomeda, a galaxy that future beings will take for granted as their home. They may never know that it was born of a collision, just as we once did not know the histories of the galaxies we observe today. For them, Milkomeda will be eternal. For us, it is a reminder that nothing in the universe is truly permanent. In this future, the galaxy will drift through a universe, growing ever darker, carrying with it the last sparks of stellar light, fading slowly into eternity. The collision that seemed violent will in the end be just one more step in the slow progression of cosmic time. Galaxies form, grow, collide, merge, and fade. The cycle continues until only darkness remains. To contemplate the fate of Milkomeda is to contemplate the fate of all galaxies, and the universe itself. The collision is not an end, nor even a beginning, but part of an endless transformation, shaped by forces that care nothing for permanence, yet create beauty at every stage of their work. At the heart of nearly every large galaxy lies a supermassive black hole, a gravitational engine, millions or even billions of times the mass of the Sun. For the Milky Way, it is Sagittarius A, a relatively quiet giant, weighing about 4 million solar masses. In Andromeda, the central black hole is even larger, perhaps 100 million solar masses. When galaxies collide, these invisible titans are brought into the same arena. Though separated by hundreds of thousands of light years at first, gravity begins to draw them together, and their eventual meeting becomes one of the most dramatic and mysterious episodes in the life of a galaxy. The process is slow. At first, each black hole continues to orbit quietly at the center of its own galaxy, drawn along with its stars as the spirals begin to merge. But tidal forces redistribute matter, and streams of stars and gas funnel inward, carrying momentum away. Gradually, the black holes approach each other, spiraling closer over millions of years. As they draw nearer, they begin to orbit one another in a cosmic dance, a binary system unlike any other. For eons, they circle, tightening their embrace, their influence reaching out across light years to shape the fates of stars caught in their gravitational fields. The region between them becomes a place of chaos. Stars that venture too close are flung outward at tremendous speeds, accelerated by the combined pull of two massive objects. Some are ejected entirely, transformed into hypervelocity stars, racing away from the galaxy at thousands of kilometers per second. Others are torn apart, their matter stretched into streams of gas that spiral inward and ignite with deadly brilliance as they fall into the hungry darkness. This stellar slingshot effect helps drain energy from the orbiting black holes,
shrinking their separation further. Every sacrificed star becomes another step toward their inevitable merger. Gas plays a more dramatic role still. During a galactic collision, gas clouds are driven toward the center, colliding and compressing until they form disks around the black hole. These accretion disks blaze with light, releasing more energy than entire galaxies. The inflow of matter can awaken a dormant black hole into a quasar, a beacon visible from billions of light years away. When two quasars ignite in the same merging system, the galaxy's core becomes a furnace of unimaginable intensity, radiating across the spectrum from radio waves to X-rays. For a time, the universe itself takes note, as two black holes prepare for their final act. And then comes the stage where space-time itself carries the burden. When the black holes close to within a fraction of a light year, their mutual orbit radiates gravitational waves, ripples in the very fabric of the cosmos. Each orbit bleeds energy away, as these waves stream outward, invisible but detectable by the most sensitive instruments ever built. Gradually, the orbit decays, faster and faster, until the two black holes spiral together in a final burst of gravitational fury. For an instant, they release more power than all the stars in the observable universe combined. Then they merge, becoming one. The event is silent in light, but thunderous in gravity, a quake that shakes space-time itself across billions of light years. Modern science has only just begun to listen to these cosmic quakes. Instruments like LIGO and Virgo have detected mergers of stellar mass black holes, each only a few dozen times the Sun's mass. Already these detections have opened a new era of astronomy. But the merger of supermassive black holes will be an event on another scale entirely. Future observatories, like the planned space-based detector LISA, may one day capture their signals, allowing us to witness the collision of galactic hearts from across the universe. Such detections would not only confirm theories of general relativity on the grandest scales, they would reveal the hidden history of galactic evolution itself. The aftermath of a supermassive black hole merger is no less astonishing. The newly formed black hole may recoil from the combined momentum of the event, kicked across thousands of light years at speeds great enough to displace it from the galactic core. Some may even be ejected entirely, drifting alone through intergalactic space. Others settle into the center of the merged galaxy, their mass swollen, their hunger insatiable. Around them, stars swirl in chaotic orbits, and the galaxy reshapes itself around the new gravitational monarch. For billions of years afterward, this single black hole will dominate the fate of its surroundings, its power a lasting echo of the collision that created it. Speculation stretches further still. Could civilizations near such a merger endure its effect? The radiation from an active quasar could sterilize regions of the galaxy, bathing worlds in deadly energy. Yet far enough from the core, life might continue, bearing witness to skies filled with strange lights and unfamiliar brilliance. Advanced beings aware of their black hole's impending merger might even learn to anticipate the flood of gravitational waves, seeing them not as destruction, but as opportunity, a source of knowledge, or even of power if such forces could ever be harnessed. For them, the collision of black holes would not only reshape their galaxy, but redefine their understanding of existence. In the grand picture, these mergers are more than rare curiosities. They are essential steps in the growth of galaxies. Just as spirals combine to form ellipticals, their central black holes combine to form ever larger singularities. Over cosmic time, these objects grow from millions to billions of solar masses, shaping their galaxies with winds, jets, and radiation. Without them, galaxies would not evolve as they do. Their hunger regulates star formation, their gravity sculpts stellar orbits, their energy flows determine what gas is lost and what remains. The black holes are not passengers in the cosmic story of collision. They are authors, writing new chapters with every union. And so in the future collision of the Milky Way and Andromeda, the drama at the center may prove the most profound of all. When Sagittarius A meets Andromeda's black hole, they will spiral together in a dance unseen but not unfelt, shaping the very fabric of space-time. Long after our stars have shifted, long after constellations have vanished, the heartbeat of this cosmic union will echo outward in gravitational waves, a signal of creation born from collapse. For the universe, it is another moment in an endless cycle. For us, it is a reminder that even in silence, the cosmos speaks, and when galaxies collide, their black holes sing the loudest song of all.
When galaxies collide, the drama does not unfold in isolation. They are not solitary wanderers drifting alone through the void. Every galaxy, is part of a larger community, groups, clusters, and vast filaments that weave the universe into a cosmic web. The Milky Way and Andromeda are members of the local group, a small gathering of more than 50 galaxies bound together by gravity. Beyond this group lies the Virgo cluster, a colossal collection of thousands of galaxies. And beyond that, still greater structures stretching across hundreds of millions of light-years. To understand galactic collisions fully, we must see them as threads in this vast fabric, shaping not just individual galaxies, but the architecture of the cosmos itself. The universe on its largest scales is not random. Observations reveal a structure resembling a web, long filaments of galaxies stretching across space, intersecting at dense nodes where clusters form. Between these filaments lie enormous voids, regions nearly empty of galaxies at all. This pattern emerged in the early universe, from the distribution of dark matter, which pulled matter into strands and knots as the cosmos expanded. Over billions of years, galaxies formed within these filaments, and collisions became the means by which small structures built larger ones. In this way, every galactic merger is not just a local event, but a step in the growth of the cosmic web itself. Clusters of galaxies provide some of the most spectacular examples of collisions. Within a cluster, galaxies are crowded together, moving at thousands of kilometers per second through a common halo of dark matter and hot gas. Collisions are frequent, and the evidence is dramatic. Spiral galaxies are twisted and stripped, their gas stolen by the cluster's hot plasma. Others are shredded entirely, leaving only faint streams of stars behind. In some cases, galaxies collide not one at a time but in great waves, as entire groups plunge into a cluster's core. The result is a constant reshaping of the galaxies within, turning vibrant spirals into red ellipticals, fueling bursts of star formation, and awakening dormant black holes. On even larger scales, clusters themselves collide. When two clusters meet, each carrying thousands of galaxies and immense halos of dark matter, the result is one of the most violent events in the universe. Gas clouds slam together, creating shock waves that stretch for millions of light-years. Galaxies pass through one another like sparks in a storm, while their dark matter halos interpenetrate, guiding the collision's outcome. These events reshape the structure of entire regions of space, fusing smaller clusters into giants that dominate their surrounding. The largest structures we see today, superclusters like Laniakea, of which our local group is a part, are the products of countless such mergers across cosmic time. The fate of our own local group is entwined with this larger picture. The Milky Way and Andromeda will merge to form Milkomeda, but that is only the first step. Over billions of years, Milkomeda will drift toward the Virgo cluster, drawn by its immense gravity. The local group itself may one day collide with Virgo, fusing into a still greater structure. The galaxies we know today, even in their merged form, will become part of something larger still, a single massive cluster in which individual histories are lost to the collective. This is the destiny of galaxies, to combine, merge, and grow into ever greater structures, until the universe's expansion isolates them forever. Dark energy complicates this destiny. As the universe expands at an accelerating rate, distant clusters are carried away faster than gravity can draw them together. On small scales like groups and nearby clusters, gravity still dominates, and collisions will continue. But on the largest scales, expansion wins. Superclusters that are bound together now will eventually be cut off from one another, isolated islands adrift in the cosmic sea. The collisions of the future will be local, confined to clusters and groups, while the rest of the universe slips beyond the horizon of observation. This means that while the cosmic web is visible to us now, in trillions of years it will be invisible, its threads stretched beyond reach. Still, within these bound islands, collisions will go on. Milkomeda may eventually merge with other galaxies in the local group, then with Virgo, and so on, until a massive elliptical galaxy dominates our region of space. Its stars will age and fade, its black holes will merge and grow, and its structure will stabilize into a single enormous remnant. From within, future observers may see only this galaxy, unaware that it was once a cluster of thousands. Their night sky will be filled, not with spirals or clusters of galaxies, but with a single overwhelming presence, the last beacon of structure in a darkening universe. The role of collisions in shaping the large-scale structure of the cosmos cannot be overstated. They are the mechanism by which small galaxies become giants, by which clusters form, and by which the web itself evolves. Without them, the universe would be a scattered collection of small dim systems, never growing into the grand architecture we see today. Collisions are the builders of cosmic order, the sculptors of the universe's greatest structure. Every filament, every cluster, every supercluster owes its existence to billions of years of galaxies, colliding, merging, and reshaping one another. And yet, in the end, the scale of these events dwarfs our ability to comprehend them fully. To speak of two galaxies colliding is already beyond the human imagination. To speak of two clusters colliding, or two superclusters, is to speak of distances and times so vast that they resist every metaphor. What happens when galaxies collide is more than a story of stars and gas. It is the story of how the universe itself has grown, from its first sparks of structure to the web we see today, and how it will continue to change until expansion leaves us in cosmic solitude. The collisions of galaxies are not isolated accidents. They are the threads from which the fabric of the cosmos is woven. And as we look outward, tracing the filaments of the web across billions of light years, we are also looking backward in time, seeing the echoes of collisions that shaped everything we know. In those collisions lies the history of the universe and its future. In the distant future, when the Milky Way and Andromeda finally meet, the fate of stars and planetary systems will depend less on violent crashes than on subtle gravitational shifts. Galaxies are mostly empty space. Stars, though numbering in the hundreds of billions, are spread so far apart that the chances of two colliding directly are astronomically small. Yet while physical collisions are rare, gravitational encounters are inevitable. The orbits of stars will be stretched, twisted, and redirected as the immense gravitational tides of two galaxies ripple through their disks. And in those quiet but relentless shifts, the fates of countless worlds will be decided. Imagine our sun as Andromeda approaches. At first, nothing seems to change. The night sky still holds familiar constellations, though over thousands of years they drift subtly out of place. Then, over millions of years, Andromeda grows brighter and larger. It becomes more than a faint smudge. It blooms into a sprawling spiral that dwarfs the Milky Way's band. Stars from its arms begin to pepper the sky, mixing with our own, until the heavens are crowded with unfamiliar light. During this time, the sun and its planets continue their orbit around the galactic center. But that orbit is no longer stable. The pull of Andromeda begins to tug, nudging the solar system onto a new path. For most stars, these changes will mean relocation rather than destruction. The simulation suggests that many will be pushed into elongated orbits that carry them far into the outskirts of the merged galaxy. Some will be drawn closer to the core, pulled into regions more crowded with stars and bathed in the light of quasars, igniting during the merge. A small fraction will be flung entirely free, hurled into intergalactic space as rogue stars. These exiles will drift alone, carrying their planets with them into eternal night. For any life clinging to such worlds, survival would mean enduring in a cosmos stripped of every familiar landmark, their sun a solitary point adrift between galaxies. Within star systems, the danger comes from near encounter. When stars pass close to one another, close on astronomical scales, meaning within a few light years, their gravitational pull can destabilize planetary orbit. A planet that once circled its sun serenely for billions of years might be nudged into a wider orbit, or a more eccentric path that freezes and scorches it in turn. Some may be torn free entirely, cast out as rogue planets. Others may be drawn into fatal spirals, falling into their parent star, or colliding with sibling worlds. Such encounters will be rare, but in a galaxy of hundreds of billions of stars, even rare events translate into countless disrupted systems. Gas clouds, far larger and more vulnerable than stars, will collide head-on. Their compression will ignite bursts of star formation, lighting the skies with brilliant clusters of young, blue stars. For civilizations that survive to witness this epoch, the heavens will blaze with new suns scattered across every horizon. The night sky will no longer be dark and serene but restless, alive with the birth of stars and the afterglow of supernovae. Entire constellations could be reshaped in a single lifetime, as new clusters outshine the old. What to us now seems like the slow and patient rhythm of the cosmos
will for them become an era of visible transformation. The sun itself is unlikely to collide with another star, but its destiny is less certain when the galactic merger begins in earnest. Simulations suggests that it could be cast outward into the halo of the new galaxy, where the stars are thin and sparse, and the night sky is dimmer. Or it could find itself pulled closer toward the core, into a region flooded with radiation from supermassive black holes, feeding on infalling gas. If the sun is drawn inward, Earth and its fellow planets, if they still exist, may be bathed in radiation that sterilizes them completely. If it is pushed outward, they may drift in lonely obscurity, orbiting quietly in the cold, thin outskirts of Milkomeda. Yet Earth itself may not endure to see that. By the time the Milky Way and Andromeda collide, roughly 4 to 5 billion years from now, the sun will be nearing the end of its stable life. It will swell into a red giant, boiling Earth's oceans and stripping away its atmosphere. Long before the galaxy itself is reshaped, our world may already be lifeless. But other planets, farther from their stars, may bloom into habitability during this time. Moons that were once frozen may thaw in the warmth of swelling suns. New cradles of life could emerge even as old ones vanish. For the universe, the end of one habitable world is not tragedy, but transition. The broader fate of life during a galactic collision is a tantalizing question. If intelligent civilizations exist elsewhere in the Milky Way or Andromeda, the merger would not escape their notice. They would see the approach of another galaxy across their skies, just as we do, and know what it means. For them, the question would not be what happens in theory, but what to do in practice. Do they prepare to abandon unstable stars, moving to safer orbit? Do they spread across their galaxy, seeding new worlds in hopes that some will survive? Or do they accept the inevitability of cosmic change, living their brief span beneath skies they know will not last? Perhaps this is the greatest paradox of galactic collision. On the one hand, they are slow, unfolding across spans of time so vast that no single species could witness them from start to finish. On the other, their consequences are deeply personal, altering the fate of stars, planets, and possibly civilization. The merging of the Milky Way and Andromeda will not simply be an astronomical event. It will be a transformation of every world within them, a reshuffling of destinies, written not in myth, but in gravity. And as we contemplate this future, one fact remains clear: the universe is not static. What seems eternal is only temporary. The night sky itself, the canvas on which humanity has painted its myths and stories for millennia, is in motion. In the future, it will not resemble what we see today. Galaxies will merge, stars will shift, constellations will vanish, and new ones will be born. To ask what happens when galaxies collide is to ask what happens when the universe itself changes shape, and to remember that we too are caught within that transformation. Long before the Milky Way and Andromeda existed, long before spirals and ellipticals filled the cosmos, the first galaxies were already colliding. In the early universe, collisions were not rare, isolated events. They were the very mechanism of creation. The cosmos had begun as a near-uniform sea of hydrogen and helium, with only tiny ripples in density seeded by quantum fluctuations during inflation. Over time, gravity amplified those ripples. Matter collected, clumped, and collapsed, forming the first dark matter halo. Into these halos, gas flowed, cooling and igniting the first stars. These were small, primitive galaxies, mere fragments compared to the giants we see today. But from the very beginning, their growth depended on mergers. In that epoch, collisions happened far more frequently than they do now. The universe was denser, its structures closer together, and galaxies much smaller. Every merger brought dramatic consequences. The first stars, massive, hot, and short-lived, exploded as supernovae, enriching their surroundings with heavy elements for the first time. When galaxies collided, their gas compressed into bursts of star formation, lighting up the early cosmos. These events were not just spectacular, they were essential. Without them, there would be no carbon, oxygen, iron, no building blocks for planets, no chemistry of life. Collisions were the crucibles in which the universe forged its own complexity. Astronomers studying the most distant galaxies, whose light has traveled for more than 13 billion years to reach us, often find irregular, chaotic shapes. Unlike the graceful spirals or smooth ellipticals nearby, these ancient galaxies look clumpy, disturbed, torn apart. Many are caught in the act of merging, their forms distorted by tidal force. This suggests that mergers were not occasional disruptions, but the dominant mode of growth in the early universe. Galaxies were assembled piece by piece, smaller fragments colliding and fusing again and again, until they became the massive systems we know today. Our own Milky Way was born from countless such mergers, its stars carrying the memory of collisions that happened long before Earth existed. The oldest stars in the Milky Way tell this story. Some orbit in the halo, moving along paths that betray their origin in long-destroyed galaxies. Others belong to stellar streams, ghostly rivers of stars that stretch across the sky, remnants of smaller galaxies, torn apart by our own. Each stream is evidence of a merger, a scar left on the Milky Way's body by encounters billions of years ago. To study these stars is to reconstruct the hidden history of our galaxy, to see that it was not born whole, but assembled from fragments across cosmic time. Every star we see in the night sky is part of this inheritance, a witness to the mergers that built our home. Even the Milky Way's structure reflects this violent past. Its thick disk, populated by older stars, may have formed when an ancient merger stirred the galaxy, puffing it up. Its halo is littered with the debris of smaller galaxies, like the Sagittarius dwarf, which is still being devoured today. The Andromeda Galaxy shows similar scars, its outer regions shaped by past collisions. Both galaxies are monuments to a history of mergers, stretching back to the dawn of the universe. Their future collision is not an exception, but the latest chapter in a long tradition, written by the relentless hand of gravity. Supermassive black holes, too, were products of this early chaos. Seeds of black holes, formed from the collapse of the first massive stars, grew rapidly during mergers. Gas funneled inward by collisions fed them, and each merger brought black holes together, combining into larger and larger singularity. By the time the universe was less than 1 billion years old, quasars already blazed across the cosmos, powered by black holes with billions of solar masses. Their existence is a testament to the speed and violence of early mergers, which fueled growth at rates almost unimaginable. Without collisions, such giants could not have formed so quickly. The cosmic web itself, that vast network of filaments and clusters, is the product of mergers on every scale. Small halos merged into larger halos, groups merged into clusters, and clusters merged into superclusters. The universe we see today, with its grand architecture stretching across hundreds of millions of light years, is the direct descendant of those early collisions. The patterns of galaxies, the richness of clusters, even the emptiness of voids, all are shaped by a history of matter flowing, merging, and reorganizing under gravity's influence. Collisions are not interruptions of the cosmic order, they are the mechanism by which order emerges. And yet, in contemplating this history, we face a striking realization. The universe is now quieter than it once was. Galaxies are larger and farther apart, collisions less frequent. The great age of assembly is over, and what we see now are the final stages. The merging of spirals into ellipticals, the last bursts of star formation, before the fuel is gone. The early universe was wild and chaotic, a place where galaxies collided constantly, growing in fits and starts. The present is calmer, more sedate, but still shaped by the echoes of that turbulent youth. The future, too, will be quieter still, as galaxies fade into isolation under the grip of dark energy. In a way, to study collisions in the early universe is to study our own origin. The atoms in our bodies were forged in stars, born of those mergers. The sun itself formed from gas, enriched by countless past collisions. Even the stable orbit of Earth is possible only because of the way the Milky Way grew, its structure shaped by ancient mergers. We are not merely observers of this history, we are products of it, walking evidence of collisions that happened billions of years before life began. The story of galaxies is our story, written not in words but in stars and gas, in black holes and dark matter, in the restless motion of the cosmos. And so, when we look at the faint smudges of ancient galaxies on the edge of the observable universe, we are not just peering into the past, we are peering into the furnace that made us. Every collision we see there is a step in the chain that leads, ultimately, to us looking back. The question of what happens when galaxies collide is not only about the fate of distant stars or cosmic structures. It is about how the universe built itself, how it gave rise to complexity, and how it set the stage for life to wonder at its own beginning. The story of galactic collisions is not confined to theory and simulation. Across the night sky, evidence of these encounters is written in light for those who know how to read it. Astronomers have spent decades unraveling the signatures of mergers, using telescopes that see not only visible light but also radio waves, X-rays and infrared. What we know about collisions comes not just from equations and computer models, but from direct observation of galaxies caught in the act, their shapes distorted, their stars flung into great arcs, their gas ignited into bursts of furious creation. To study these cosmic events is to witness the universe mid-transformation, frozen in different stages, across billions of light years. One of the clearest signs of a collision is the presence of tidal tails, enormous streams of stars and gas, pulled from galaxies by gravitational forces. These tails stretch for hundreds of thousands of light years, curling through space like luminous ribbons. Famous examples include the antennae galaxies, two spirals in the process of merging, their arms flung outward into spectacular arcs. In them we see the choreography of gravity laid bare, the invisible tug-of-war made visible in light. Observing such systems allows astronomers to reconstruct their histories, where the galaxies came from, how they interacted, and what their ultimate fate will be. Beyond visible light, other wavelengths reveal the hidden consequences of collisions. Radio telescopes detect the jets of plasma fired from active galactic nuclei, powered by black holes awakened by merger. Infrared observatories, like the James Webb Space Telescope, peer through dust to see the starbursts triggered by colliding gas clouds, uncovering clusters of newborn stars hidden from ordinary sight. X-ray telescopes observe the hot gas, shocked and heated during the encounters, glowing with energies invisible to human eyes. By combining these observations, astronomers build a multi-layered picture of galactic collisions, each wavelength adding another dimension to the story. Perhaps the most striking tool of all is the ability to look back in time. Because light takes billions of years to travel across the universe, distant galaxies show us collisions as they happened long ago. When we observe a galaxy 10 billion light-years away, we are seeing it as it was when the universe was young, in an era when collisions were far more common. In this way, the night sky becomes a time machine, its faint smudges revealing the entire history of galactic evolution. By collecting thousands of such images, astronomers can piece together the life cycle of collisions, from first approach to final merger, across the ages of the cosmos. Simulations bring these observations into sharper focus. Using supercomputers, scientists model the gravitational interactions of billions of stars, tracing how galaxies deform and merge. These simulations, when compared to real images, reveal astonishing accuracy. The shapes of tidal tails, the timing of starbursts, the awakening of black holes, all match what we see in telescopes. Together, observation and simulation form a dialogue. Telescopes provide snapshots, and models fill in the motion, showing how those snapshots fit into a continuous story. In this way, astronomers can predict not only the fate of galaxies we observe, but also our own. The Milky Way's destiny with Andromeda has been studied in just this way. Careful measurements of Andromeda's motion, combined with simulations of the interaction, suggest the first close approach will occur in about 4 billion years, with full merger following over another 2 billion. The result will be a massive elliptical galaxy, just as theory predicts. Observing collisions elsewhere in the universe provides a preview, a way to see what our own sky may look like in the distant future. Every image of merging spirals is a mirror, showing us what is to come. Even within our galaxy, evidence of past collisions can be observed. Surveys like Gaia map the motions of stars with extraordinary precision, revealing streams and clumps that betray their origins in smaller galaxies long ago absorbed by the Milky Way. Each stellar stream is a fossil, a trace of a collision that happened billions of years ago. By following these streams across the sky, astronomers reconstruct the Milky Way's assembly, identifying the remnants of galaxies that no longer exist as independent systems. The Sagittarius dwarf galaxy, now being torn apart, is only the latest in a long series of victims. Our home has been growing through collisions since its birth. The ultimate confirmation of galactic collisions comes not in light, but in gravity itself. Gravitational waves, ripples in space-time, offer a new way of observing mergers, not of galaxies directly, but of the black holes they contain. Already, detectors have recorded waves from the mergers of stellar mass black holes, but the future promises more. Space-based observatories will be able to detect the slower, deeper waves from supermassive black holes, spiraling together during galactic merge. When that happens, humanity will hear the universe in a new way, listening to the very fabric of space-time as galaxies collide. It will be a kind of astronomy no one could have imagined a century ago. For now, we are still learning to interpret what we see. Each collision is unique, shaped by the masses of the galaxies involved, their gas content, their relative angles, and their speeds. Some produce dazzling starbursts, others only subtle distortions. Some awaken black holes into quasars, others leave them dormant. The diversity of outcomes reflects the complexity of the universe itself. No two collisions are the same, yet all obey the same physical laws. Gravity, gas dynamics, and dark matter orchestrate every encounter, weaving chaos into patterns that repeat across billions of light years. To observe galactic collisions is to watch the universe at work, reshaping itself in slow but dramatic fashion. For astronomers, these events are not just spectacular, but essential, windows into how galaxies grow, how stars form, and how black holes evolve. For us, they are also a reminder that the universe is not static. The night sky we take for granted is a fleeting arrangement, already changing beneath our gaze. One day, far in the future, our own sky will bear the unmistakable mark of collision. Until then, we watch others and learn, piecing together a story that is both vast and intimate, stretching from the first galaxies to the final fate of our own.
For those who might one day gaze upward from some surviving world in the Milky Way, the merger with Andromeda will not be an abstract concept or a scientific prediction. It will be written directly across their sky. A transformation unfolding slowly but unmistakably over millions of years. The night sky will not merely shift. It will become unrecognizable, filled with shapes and lights that no human today has ever seen. To imagine that future is to step into the perspective of observers who, if they exist, will live through one of the most extraordinary spectacles the universe can provide. At first, Andromeda will be only a faint smudge of light, as it is today, but over hundreds of thousands of years, its glow will intensify. Across millennia, its disk will grow larger, spreading out across a swath of the heavens. Where we now see only a hazy oval, future eyes will see spiral arms, clusters of stars and dark lanes of interstellar dust, stretched out in intricate detail. The Milky Way itself will no longer be a solitary band across the night, but a partner in a celestial dance, its form mirrored and challenged by another great spiral encroaching on the sky. As the galaxies approach, the transformation will accelerate. Constellations familiar for millions of years will dissolve as stars shift against the backdrop of Andromeda's growing face. New stars, drawn from gas clouds compressed by tidal forces, will ignite across the heavens, adding brilliance to the night. Regions of the sky will blaze with clusters of hot blue stars, each shining more brightly than entire constellations do today. Supernovae will punctuate this drama, their sudden outbursts briefly outshining all others. For future observers, the night will be restless and alive, a sky that changes not only across generations, but within a single lifetime. When the first close passage occurs, the spectacle will defy imagination. Andromeda will stretch across the entire sky, a luminous whirlpool of stars, dwarfing the moon, and even the Milky Way itself. Great arcs of stars, pulled into tidal tails, will sweep across the heavens like glowing rivers. Dark nebulae, silhouetted against these rivers, will drift like shadows across a cosmic canvas. For those who survive to see it, the sky will no longer be a distant panorama of points, but a living map of galactic anatomy, visible in sprawling grandeur. The heavens will become a theater of cosmic scale. Not all vantage points will be equally safe. Civilizations near the galactic center may find themselves bathed in intense radiation, as gas funnels inward to feed supermassive black holes. Their skies may blaze with quasars, drowning out starlight and deadly brilliance. Others, orbiting stars in the outer reaches, may see the collision as a distant ballet, their worlds spared the worst, but still witness to a spectacle of unparalleled beauty. For them, survival may depend less on avoiding destruction than on enduring through time, watching the dance unfold across countless generations. As the merger continues, the structure of the sky will grow chaotic. Two disks will interpenetrate, stars from Andromeda mixing with stars from the Milky Way. The idea of distinct galaxies will vanish for observers living through the middle stages. Instead, the heavens will appear filled with overlapping patterns, luminous knots, and shifting arc. The very concept of a fixed constellation will become meaningless. The night will be a place of constant change, a reminder of impermanence etched into every horizon. Eventually, the galaxies will settle into a new form. The spirals will be gone, replaced by a vast elliptical glow, stretching across the heavens. The night sky will no longer have a band like the Milky Way. Instead, it will be suffused with a uniform haze, brighter and denser toward the center, but spread across the entire sky. For those who inherit this era, the memory of spirals will be only history, preserved in records if they survive. Their home galaxy will not be a disk but a spheroid, and their place within it will be defined by a new celestial order. If intelligent beings look outward in that future, their interpretation of the cosmos will differ profoundly from ours. For us, the visible universe is filled with galaxies, billions of them spread across the night in deep imaging. But for them, the accelerating expansion of the cosmos will have carried distant galaxies beyond visibility. By the time Milkameda has fully formed, it may be the only galaxy they can see. Their skies will blaze with stars, but their telescopes will find only darkness beyond. For them, the story of cosmic collisions will not be a general principle but a singular event, their own galaxy's history, written into its shape. To imagine this perspective is to realize how much of our understanding depends on the epoch in which we live. We see a universe filled with galaxies because we happen to exist in a time when light from them still reaches us. We know about collisions because we can observe them happening elsewhere. In the distant future, such evidence will vanish. Observers then will know only their own galaxy, a merged giant drifting alone in the void. Their science may never uncover the true vastness of the cosmos. To them, Milkameda will be the universe. Yet for those who watch the collision unfold, the sky will speak more directly than any theory could. They will see two galaxies become one, the heavens themselves reconfigured before their eyes. They will live beneath skies filled with reminders that the universe is alive, dynamic, and impermanent. For them, the lesson of collisions will not be hidden in faint smudges, billions of light years away, but blazoned across every horizon. Their myths, their sciences, their philosophies will all be shaped by the vision of galaxies merging above their head. Perhaps that is the true power of imagining this future. To recognize that the sky we know is not eternal, that it will be remade, and that others, if they exist, will inherit a universe very different from ours. To them, the collision will not be prediction, but memory. For us, it remains a story glimpsed in the light of distant galaxies, a future we will never see but which nonetheless defines our place in the cosmos. What happens when two galaxies collide is not only the rearrangement of stars and gas, it is the rewriting of the sky itself, and with it, the way beings within that sky understand the universe. In the far future, long after the merger of the Milky Way and Andromeda has settled into the massive elliptical remnant we call Milkameda, the galaxy will continue to evolve. Its stars will age, its light will slowly dim, and its relationship to the rest of the universe will change in ways that challenge imagination. The fireworks of the collision, the tidal tales, the bursts of new stars, the blazing activity of black holes, will fade. What will remain is a quieter, older galaxy, drifting through a cosmos that itself is changing, shaped by forces that work on scales even larger than galaxies. The story of Milkameda is not only one of creation, but also of slow decline, a journey toward solitude and silence. Once the merger is complete, star formation will continue for a time, fueled by the gas clouds compressed during the encounter. Great clusters of blue stars will shine for tens of millions of years, lighting the galaxy with brilliance. But these young stars will burn through their fuel quickly, living fast and dying young. In their place, the longer-lived stars, yellow dwarfs like the Sun, orange dwarfs, and the countless faint red dwarfs will dominate. These will be the main inhabitants of Milkameda for billions, even trillions of years to come. Their light will be dimmer,
but they will endure long after the spectacular giants have vanished. The galaxy will settle into a quieter glow, no longer fiery but steady, a hearth instead of a blaze. Eventually, the gas supply will be exhausted. The collisions of gas clouds that once fueled star formation will subside, leaving little material for new stars to form. This is the fate of elliptical galaxies we already observe across the universe. They are filled with old stars, but bereft of gas, their youth long behind them. Milkamada will join their ranks, becoming what astronomers call reddened. The galaxy will shine with the combined light of ancient stars, but its days of creation will be over. No new suns will rise. Only the slow aging of those already born will continue. As the stars age, their individual stories will shape the galaxy. Massive stars will collapse into black holes, and neutron stars, scattered like embers across the void. Smaller stars will expand into red giants, shed their outer layers, and leave behind white dwarfs, dense, cooling remnants that will glow faintly for trillions of years. Over time, white dwarfs will fade into black dwarfs, invisible cinders in the dark. Red dwarfs, the most common stars in the universe, will burn steadily for trillions of years, providing the last flickers of starlight in an aging galaxy. The sky of that far future will not be filled with dazzling constellations, but with a more uniform, dim, red glow, the afterlight of a universe growing old. While the stars evolve, the galaxy itself will drift into cosmic isolation. The expansion of the universe, driven by dark energy, is accelerating. Distant galaxies are receding faster and faster, and over time more and more will slip beyond the horizon, carried away so quickly that their light will never reach Milkamada. Already billions of galaxies are receding at incredible speeds. In tens of billions of years, only those bound to the local group will remain visible. Eventually, even the Virgo cluster, once the nearest large collection of galaxies, will disappear beyond. Milkamada will stand alone in the observable universe, a solitary island of light in an infinite dark. For any observers alive in that era, the cosmos will look profoundly different. The sky will still be filled with stars, but beyond their galaxy, nothing. No spirals, no clusters, no faint smudges on the horizon. The evidence of the Big Bang, the cosmic microwave background radiation, will have redshifted into wavelength, so vast that no instrument could detect it. The record of cosmic history will be erased by expansion. Future astronomers may look out and see only Milkamada, assuming it is the entire universe. They will not know the truth we glimpse today, that billions of galaxies once filled the skies, that the cosmos was born in fire, and that they are living in the final flickering age of starlight. Within Milkamada, gravity will continue to shape the fates of stars and black holes. Over unimaginable spans of time, stars will be scattered by encounters, some ejected into intergalactic space as lone wanderers. The central black hole, swollen by the merger of Sagittarius, 8, Andromeda's supermassive black hole, will dominate the core. It will continue to consume gas and stars that venture too near, growing ever larger. Over trillions of years, it may become one of the most massive objects in the universe, a singular anchor in a galaxy of fading light. As time stretches on, the galaxy will become quieter still. Star formation will cease entirely. The once bright elliptical will fade into a dim collection of remnants, its glow visible only to those nearby. Its stars will grow colder, its white dwarfs darker, its black holes and neutron stars more isolated. Eventually, the galaxy will be populated mostly by faint red dwarfs and the dead husks of stars long extinguished. It will persist, bound together by dark matter, but its days of brilliance will be only memory. In this vision of the far future, Milkamada becomes a symbol of the universe itself, born in fire, matured in collisions, and destined for silence. The great drama of galaxies colliding will give way to the quiet persistence of remnants, then finally to the fading of all light. Yet even in this fate, there is a strange beauty. The universe is not static but alive, changing across every scale of time and space. What happens when galaxies collide is not merely destruction, but transformation, creating new structures, new histories, and new meanings, even as everything moves inexorably toward the dark. For us, living in a universe still rich with galaxies, it is almost impossible to imagine that future, but to contemplate it is to recognize the fragility of our moment. We exist in an age where the cosmos is still visible, where the web of galaxies still shines across the sky, and where the story of collisions can still be read in light. That window will not last forever. The story of Milkamada is not only a prediction of what is to come, but a reminder of how rare it is to see the universe as it truly is. The story of galactic collisions does not end with the fading of galaxies into quiet giant. It continues, stretching into the deep future of the cosmos, far beyond the lifespan of any star we know today. If we follow Milkamada across trillions of years, through the slow extinguishing of its light, we arrive at an era often called the Degenerate Age, when the bright drama of stars has ended, and the universe is ruled by remnant. To contemplate this epoch is to step into timescales so immense they seem almost unreal, yet they are the inevitable continuation of the processes we already see unfolding. In the first trillions of years after the last great bursts of star formation, Milkamada will be a galaxy of endurance. The faint red dwarfs, small, steady stars burning their fuel with extraordinary efficiency, will dominate. Unlike the massive stars that burn bright and die quickly, red dwarfs can live for trillions of years, slowly sipping their hydrogen. Their dim reddish glow will sustain the galaxy long after brighter stars have faded. Around them, planets may orbit in quiet obscurity, bathed in pale light, potential havens for life long after Earth and its sun are gone. For an almost inconceivably long stretch of time, these faint stars will keep the galaxy alive. But eventually even the red dwarfs will exhaust their fuel. When they do, they will contract and fade into white dwarfs, joining the countless others that already populate the galaxy. The universe will then enter a time without active star formation, a cosmos filled only with the remnants of stars. White dwarfs will cool slowly, their heat radiating into space over quadrillions of years. One by one, they will dim, turning from white to red to black, becoming inert husks known as black dwarfs. At that point, the galaxy will no longer shine. Its light will be gone, replaced by the invisible cinders of stars that once illuminated the night. Yet even in darkness, the galaxy will not be static. Gravity will continue its patient work. Stellar remnants will scatter off one another, altering their orbits. Some will be ejected entirely, hurled into intergalactic space as rogue black dwarfs and neutrons. Others will spiral inward, pulled toward the central black hole. Collisions of remnants will occasionally spark new bursts of energy. Two white dwarfs, merging into a brief supernova, or neutron stars, colliding in titanic explosions that briefly light up the void. But these events will grow rarer with time, until the galaxy becomes a place of almost total silence, disturbed only by the faint gravitational motions of its remains. At the heart of Milkamada, the supermassive black hole will continue to reign. It will consume stars and remnants that stray too close, growing ever larger. Over unimaginable stretches of time, it could become one of the most massive objects in existence, a monster containing billions of solar masses. And it will not be alone. Smaller black holes formed from the collapse of massive stars during the galaxy's earlier brighter days will roam the galactic halo. Some will merge with one another, creating bursts of gravitational waves that ripple across space, even in an era when no light remains. In the darkness, black holes will be the last active players, shaping the fates of the galaxy's remnants. But black holes too are not eternal. According to the theory of Hawking radiation, they slowly lose mass over time, emitting faint particles of energy. For stellar mass black holes, this process takes longer than the current age of the universe, by many, many orders of magnitude. Supermassive black holes will last even longer, their evaporation stretching across a timescale of 10 to 100 years, or more. Yet given enough time, they too will vanish. The titans that once devoured stars and ruled galaxies will dissolve into nothingness, their mass radiated away into the dark. The last echoes of collisions, the final remnants of galactic history, will disappear into the background. What remains then is a universe that has outlived its galaxy. A cosmos filled not with light, but with particles drifting in near-perfect emptiness. The great structures of the cosmic web will have unraveled, the galaxies themselves evaporated into their components, the stars extinguished. The universe will enter its final era, an age of expansion, without renewal, of entropy creeping toward its ultimate maximum. This is the heat death, a future in which energy is spread so thinly and evenly that no new structures, no new stars, no new collisions are possible. The universe will be vast, dark and silent, its history buried in frozen remnants and fading radiation. And yet, even in this bleak vision, There is a strange poetry. The galaxies that once collided, merged and blazed with light, were not destroyed in vain. Their interactions forged the elements, built the stars and created the conditions for life. Their collisions lit the skies of countless worlds, and may have given rise to civilizations who pondered their meaning. Every black dwarf and black hole in the distant future is a monument to those earlier times, a reminder that the cosmos was once alive with brilliance. The silence of the future is the echo of a past filled with light. For us, living at the dawn of cosmic maturity, this future is not something to fear, but to marvel at. We exist in a fleeting window, when galaxies are still visible, when stars still shine, and when the story of collisions can be told in light instead of whispers of remnants. We can look outward and see the universe in motion, galaxies colliding, merging and transforming, knowing that we live in an age when such knowledge is possible. The deep future will not allow such views. It belongs to a cosmos where the evidence has been erased. That makes our perspective both fragile and precious. So, what happens when two galaxies collide? The answer stretches from the immediate spectacle of tidal tails and starbursts, through the long decline into elliptical giants, and into the unimaginable future of darkness and silence. Collisions are not only events of destruction, they are the architects of the universe's history, shaping everything from the atoms in our bodies to the fate of the last black hole. The universe begins in light and ends in darkness, but in between it creates wonders, galaxies, stars, planets, and perhaps even beings who dare to ask these questions. When galaxies collide, it is not only stars that are scattered or black holes that awaken. It is chemistry itself that is transformed. In the violence of these encounters, the raw ingredients of life are forged, scattered and concentrated in ways that shape the very possibility of existence. Without collisions, the universe might still be filled only with hydrogen and helium, the simple gases born in the Big Bang. It is through the chain of star birth, star death, and the compression of gas during galactic mergers that heavier elements emerge: the carbon in our cells, the oxygen we breathe, the iron in our blood. To ask what happens when galaxies collide is also to ask how the universe creates the building blocks of life. In the earliest days of the cosmos, the first stars burned quickly and brightly, fusing hydrogen into helium, then helium into heavier elements. When these massive stars exploded as supernovae, they spewed their contents into space, enriching the gas around them. But enrichment alone was not enough. For those elements to be recycled into new stars and planets, the gas had to be gathered, compressed and reignited. Galactic collisions provided the stage for this process. When gas clouds met head-on during mergers, they were shocked and compressed, triggering waves of star formation. Each new generation of stars was richer in heavy elements than the last, carrying forward the legacy of the collisions that birthed them. Over billions of years, this cycle transformed galaxies from simple structures into chemical laboratories. The spiral arms of galaxies became nurseries, where carbon, oxygen, nitrogen, silicon and iron were woven into dust grains and molecules. Collisions scattered these enriched materials across interstellar space, spreading them far beyond the stars that created them. In this way, the chaos of galactic encounters seeded entire galaxies with the potential for rocky planets, for oceans, for atmospheres. Without collisions, there might be stars, but there would not be Earths. The chemistry of life depends on violence at cosmic scale. Even within individual galaxies, we can trace the fingerprints of past mergers in the chemistry of their stars. Older stars, formed before many collisions enriched their environment, are metal poor, composed mostly of hydrogen and helium. Younger stars, born in the aftermath of countless mergers, contain far more heavy elements. Our own sun is one such star, enriched enough to form rocky planets around it. Earth's iron core, its silicon crust, and its carbon-based life are all products of galactic history. We are, in the most literal sense, children of collisions. Every breath we take carries oxygen forged in stars and scattered by galactic violence. The role of collisions in chemical evolution goes beyond enrichment. They also determine where and how life's ingredients are concentrated. Gas flows triggered by mergers can funnel material into galactic centers, feeding supermassive black holes and triggering quasars. These outbursts, though destructive, also blow enriched material into galactic halos, where it can later cool and form stars with planets. Collisions distribute the elements, ensuring that they do not remain trapped in isolated pockets, but are shared across vast scales. In a universe without collisions, enrichment would be slower, patchier, perhaps insufficient to create habitable worlds in abundance. It is worth asking whether collisions not only made life possible but shaped its distribution. Planets form from the disks of gas and dust that surround young stars. The likelihood of forming rocky planets depends on the abundance of heavy elements, and that abundance depends on how vigorously a galaxy has collided in its past. A galaxy that has endured more mergers may have more material for Earth-like planets, and therefore more chances for life. In this sense, galactic collisions are not just astronomical curiosities. They are part of the chain of causality that determines whether civilizations ever arise to contemplate them. Our own Milky Way is a case study. It has absorbed dozens of smaller galaxies over its history, each one contributing stars and enriched gas. The Sagittarius dwarf galaxy, now being torn apart, is one of the latest examples. The chemical fingerprints of its stars differ from those of the Milky Way, revealing their foreign origin. Over time, these stars will blend into our galaxy, their elements mixing into future generations of stars. Each collision is not just an exchange of mass, but of chemistry, a sharing of the essential ingredients of life. It is possible that without such mergers, the Sun might not have had enough metals to form Earth at all. The Andromeda collision will continue this story. When the two galaxies merge, their gas clouds will collide, and a burst of new star formation will follow. Many of those stars will be born with chemical abundance, even richer than ours, creating conditions for new Earths to emerge long after our own world is gone. Life, if it arises, will owe its existence to the collision itself. In this way, galactic encounters are not only destructive, but generative. They are moments when the universe reshuffles its matter, creating opportunities for complexity and perhaps consciousness. From this perspective, the violence of galaxies colliding takes on a different meaning. It is not only chaos, but creation. It is the process by which simplicity becomes complexity, by which hydrogen becomes human. The stars that explode in supernovae during collisions are tragedies on a local scale, but gifts on a cosmic one. Their ashes form the raw material for worlds, oceans, and breathing lungs. Collisions ensure that those ashes are not locked away, but shared, scattered, and transformed. The universe's greatest acts of destruction are also its greatest acts of generosity.
When we look at the faint smudges of colliding galaxies through telescopes, we are not just seeing distant fireworks, we are seeing the chemistry of our own existence in progress. The carbon that makes up our DNA was once forged in a star and scattered by events like these. The iron in our blood was once part of a galactic collision billions of years ago. Even the calcium in our bones carries the imprint of those ancient encounters. To ask what happens when galaxies collide is to trace a chain of cause and effect that stretches from the cosmic to the intimate, from supernovae to cells. And perhaps this is the deepest lesson of collisions. They remind us that we are not separate from the universe, but expressions of our existence is not an accident detached from cosmic violence, but a direct consequence of it. Galaxies collide, stars are born and die, elements are scattered, planets form, and life emerges. The story of galaxies is the story of what may seem at first like distant, impersonal catastrophes are in fact the very reason we are here to witness them. The collisions that light the universe also light our minds with the capacity to wonder. If collisions help shape the chemistry of galaxies, then they also help shape the possibility of civilizations. Life, as far as we know, depends on a delicate chain of circumstances, the right elements, the right planets, the right stars, and enough time for complexity to emerge. Collisions influence each link in this chain. They enrich galaxies with the heavy elements needed for biology, they trigger bursts of star and planet formation, and they scatter those conditions widely across cosmic neighborhoods. Without collisions, there might be stars and gas, but far fewer places where life could take hold. And so, when we ask what happens when galaxies collide, we are also asking whether collisions are the silent architects of intelligence itself. Consider how rare and precise life on Earth seems. The planet formed around a star, born in a galaxy, that had already lived through billions of years of mergers, accumulating carbon, nitrogen, and oxygen in sufficient abundance to create oceans and atmospheres. The very possibility of DNA, proteins, and cells depended on events that happened long before our solar system coalesced. Somewhere, in the overlapping histories of ancient collisions, the ingredients for life were prepared. Our planet is not an isolated miracle, but a product of cosmic history, a history written in the dance of galaxies. If this is true for us, it may be true elsewhere. Each galaxy collision in the universe is a potential seed for life. When two spirals merge and ignite bursts of star formation, countless new planetary systems are born. Among those, some may orbit stars with stable zones of warmth, some may have water and carbon, and some may evolve biology. Perhaps many remain barren, their conditions never quite right. But if even a fraction succeed, then galactic collisions could be among the most important events in shaping the spread of life across the cosmos. The merging of galaxies is not just an astronomical phenomenon, it may be a biological one. And if civilizations arise, what role do collisions play in their stories? For beings who look to the skies, the sight of another galaxy looming ever closer would be inescapable. It would dominate their myths, their sciences, their fears, and their hopes. As Andromeda approaches us, we already imagine what the future sky will look like, even though no human will be alive to see it. Civilizations elsewhere may have lived under skies filled with colliding galaxies, their very cultures defined by the drama above them. To live through such an era would be to witness creation and destruction written across the heavens every night. Collisions might also influence the survival of civilization. They can trigger starbursts, lighting up galaxies with new suns, but also increasing the frequency of supernovae and gamma-ray bursts. For worlds unlucky enough to be near such explosions, life might be threatened or extinguished. Entire biospheres could be sterilized by radiation. Yet other worlds, in calmer regions, may benefit from the abundance of new stars and planets. Collisions, then, are both threat and opportunity, destructive in some places, life-giving in others. They sculpt not only the physical galaxy, but the evolutionary pathways of life within it. It is possible, too, that civilizations may attempt to respond to the cosmic scales of these events. What would intelligent beings think, knowing that their galaxy was about to merge with another? Would they see it as doom or as destiny? Some might attempt to harness the energies released, tapping into starbursts or even black holes as power sources. Others might try to escape, building ships to move to safer regions. Or perhaps they would simply watch, creating stories and philosophies that gave meaning to the sight of their skies being rewritten. For them, collisions would not be abstract, they would be history unfolding around them. For humanity, the approaching merger with Andromeda is too distant to fear but close enough to imagine. We live at a moment when we can predict the future of our galaxy with confidence, when simulations let us see billions of years ahead. Yet we may not endure long enough to witness it directly. The civilizations of the far future, if they exist, will inherit the sky we can only imagine. For them, the collision will be as real as the moon is for us. And perhaps, if they know their history, they will understand that the very atoms they are made of were born in earlier collisions. The future they witness will be only one chapter in a story, billions of years long. And what of communication between civilizations in colliding galaxies? If life arises in both the Milky Way and Andromeda, then their eventual merger could bring them into closer contact. Signals sent across the void would arrive faster as the galaxies approached. Civilizations separated by millions of light-years could one day find themselves neighbors, watching the same collision from different vantage points. Perhaps collisions are not only chemical events, but cultural ones, bringing together minds that would otherwise have remained forever isolated. The merging of galaxies could be the merging of civilization. Or perhaps, by the time such encounters occur, civilizations will already have transcended their home galaxies, spreading across interstellar space in ways we can hardly imagine. For them, galactic collisions would be less about survival and more about opportunity, new stars to harness, new systems to explore, new frontiers opened by gravity itself. If life is persistent enough to endure cosmic timescales, then galactic collisions may not be threats at all, but milestones, moments when the universe reshuffles its cards and presents new configurations for exploration. To us, collisions may seem rare, violent, and remote. To the universe, They are natural, inevitable, and essential. They are part of the great machinery that takes simple beginnings and spins them into complexity. They are the reason that galaxies shine, that stars form, that elements exist, and that life emerges. If civilizations are scattered across the cosmos, then they too are children of collisions. Their stories, like ours, are written in the encounters of galaxies, in the scattering of gas and stars, in the enrichment of elements that make thought possible. And so, when two galaxies collide, the consequences ripple far beyond the rearrangement of stars. They shape the conditions for life, for intelligence, and for wonder. They create not just the atoms of biology, but the possibility of consciousness gazing out. Collisions are not only astronomical phenomena, they are the hidden origin stories of every civilization that looks up at the night sky and asks where it came from. To contemplate them is to recognize that we too are fragments of galaxies, meeting, evidence of a universe that builds life from chaos and gives meaning to destruction. The unseen forces that govern galactic collisions are just as important as the luminous displays we can observe. Behind every tidal tail, every burst of star formation, every black hole igniting into a quasar lies an invisible framework, dark matter. Though we cannot see it, dark matter outweighs the normal matter of stars and gas by more than 5 to 1, and it is dark matter halos that truly dictate how galaxies move, merge, and transform. To understand what happens when two galaxies collide, we must imagine not only the visible spirals clashing, but the enormous ghostly halos surrounding them interpenetrating and binding together. When the Milky Way and Andromeda meet, their disks will be the most dramatic part to our eye. But long before the stars and gas interact, the halos of dark matter will already have begun to overlap. These halos extend for hundreds of thousands of light years, invisible but massive, binding galaxies in gravitational cocoon. As they merge, they will guide the trajectories of stars, slow the galaxies through a process called dynamical friction, and ultimately ensure the collision does not end in a mere flyby, but in a full merger. Without dark matter, galaxies might not even collide as they do. It is the halos that make the encounters inevitable. This invisible scaffolding is also what explains why galaxies form structures in the first place. On the largest scales, the universe resembles a cosmic web, filaments of dark matter, stretching across billions of light years. Galaxies gather at the intersections of these filaments, drawn together by gravity. When we see two galaxies on a collision course, we are witnessing not only their local interaction, but the deeper flows of dark matter guiding them. The Milky Way and Andromeda are not randomly approaching each other. They are falling together within the gravitational basin of the local group's dark matter halo. Their meeting is written into the structure of the cosmos itself. During the collision, the influence of dark matter remains hidden yet essential. As the luminous parts of the galaxies distort and fling out tidal tails, the halos intermix, binding the stars into new orbit. The final shape of the merged galaxies, determined not only by the visible components, but by how the dark matter redistributes. Simulations that include dark matter halos reproduce the elliptical remnants we see in nature. Without dark matter, the outcomes would not match reality. It is a reminder that much of the drama we admire in galactic collisions is orchestrated by something we cannot see. The role of dark matter becomes even clearer when we study clusters of galaxies, where collisions happen on even larger scale. The Bullet Cluster, a famous example, shows the aftermath of two galaxy clusters colliding. The hot gas between galaxies collided and slowed down, glowing in X-rays, but the dark matter halos passed through almost unaffected, revealed by gravitational lensing of background galaxy. This separation between gas and dark matter is one of the strongest pieces of evidence that dark matter is real, not just a mathematical trick. Collisions in this way become laboratories not only for stars and galaxies, but for the very physics of the universe's invisible matter. Even the fates of stars in a collision are influenced by dark matter. Though stars rarely collide directly, their orbits are shaped by the gravitational potential created by both visible and invisible matter. When galaxies merge, the energy of orbital motion is transferred into random motion through dynamical friction, mediated by the halos. Over billions of years, this process transforms orderly spiral disks into the more chaotic orbits of elliptical galaxies. The elegant spirals are erased, not only because gas is exhausted,
but because the dark matter ensures that stars lose their coherent rotations. Dark matter reshapes not only the merger, but the very identity of galaxies. And beyond dark matter lies an even deeper mystery: dark energy. While dark matter binds galaxies together and makes collisions possible, dark energy drives the accelerated expansion of the universe, ensuring that galaxies not bound to us will eventually slip away beyond our view. The interplay of these two unseen forces defines the cosmic state. Within the local group, dark matter dominates, ensuring that the Milky Way and Andromeda will merge. But beyond our gravitational basin, dark energy wins, pulling galaxies apart faster than gravity can overcome. This tension between attraction and expansion dictates the history of collisions across the universe. It is striking to realize that what we can see, the stars, the gas, the dust, is only a fraction of the story. We marvel at the sight of two galaxies colliding, but what we are really seeing are tracers, luminous markers caught in a far larger and darker ballet. The halos, the filaments, the invisible scaffolding are what choreograph the dance. Our understanding of collisions is incomplete without acknowledging that we are looking at the visible skin of a much larger body, one whose bulk is hidden. To study galactic mergers is to brush against the mystery of what most of the universe is made of. Yet even as we struggle to understand dark matter and dark energy, their influence is undeniable. They shape the trajectories of galaxies, the timing of mergers, and the structures that emerge. They determine why galaxies cluster in some regions and leave voids in others, why collisions happen in the first place, and why the future of the cosmos will unfold as it does. Without them, the Milky Way and Andromeda might not be fated to merge, and the universe itself might look nothing like it does. Their invisibility does not diminish their importance. It only deepens the wonder that so much of reality lies beyond our sense. So when we ask what happens when galaxies collide, we must remember that the visible drama, the arcs of stars, the bursts of light, the blazing quasars, is only part of the picture. Beneath it all, unseen but decisive, dark matter and dark energy are shaping the story. Collisions are not just about what we can see, they are about the hidden forces that hold the cosmos together and drive it apart. In their quiet, invisible way, they are the authors of the fate of galaxies. When we look at the galaxies that populate the universe today, we are not seeing them in isolation. Every spiral, every elliptical, every irregular galaxy is a product of countless past encounters. Collisions are not rare accidents, they are the architects of galactic history, the process by which galaxies evolve, mature, and carry forward their legacy. To understand what happens when two galaxies collide is also to understand how the universe writes its history across billions of years, leaving behind visible signatures in the shapes of galaxies and the halos of stars that surround them. Elliptical galaxies, for instance, are silent witnesses to past collisions. Unlike spirals, which are structured and ordered, ellipticals are chaotic balls of stars, moving in random orbits, without the graceful arms of a disk. Their lack of cold gas, their old stellar populations, and their smooth shapes all tell the same story. These are galaxies that once collided, merged, and lost their youthful structure. Every elliptical galaxy is a fossil, the record of violent mergers that erased spirals and replaced them with something older, quieter, and more settled. When we peer through telescopes and see the giant ellipticals at the hearts of galaxy clusters, we are seeing the ultimate legacy of countless mergers, stacked over billions of years. The halos of stars that stretch around galaxies tell another story. These faint, diffuse regions are filled with stars torn from smaller galaxies. During collisions, when a dwarf galaxy falls into a larger one, it is shredded by tidal forces, its stars scattered into streams that arc across the halo. These streams can persist for billions of years, faint ribbons that betray the history of cannibalism. In the Milky Way, surveys have revealed dozens of such streams, the remnants of galaxies long absorbed. Our own galaxy is not pristine, it is a tapestry stitched together from the remains of others. Each star in the halo is a record of a collision written into the sky. Even the disks of galaxies bear scars, ripples, and asymmetries can reveal past encounters. Warps in spiral arms, rings of gas, or off-center bars are often the lingering signatures of interactions with neighbors. When we look closely, we find that no galaxy is untouched. The universe is not a place of quiet isolation, but of constant interaction. To map galaxies is to read their biographies, and collisions are the central chapters. The Milky Way's future, with Andromeda, will be one more entry in this long tradition, another event to be recorded in the shapes and motions of stars. Clusters of galaxies magnify this story. In a cluster, galaxies collide, not only with each other, but with the hot gas that fills the space between them. Shock waves ripple through this medium during mergers, heating it to tens of millions of degrees. The shapes of clusters, the arcs of gravitational lensing they produce, and the trails of stripped gas are all records of colossal collisions. These events happen on scales far beyond single galaxies, reshaping entire communities of galaxies at once. The universe is filled with archives of these encounters, written in gas, in light, and in gravity. Even on smaller scales, collisions write history. Globular clusters, dense swarms of old stars, may sometimes be remnants of ancient galaxies that fell into larger ones. The distribution of chemical abundances in stars can reveal whether they were born in the main galaxy or in a smaller one, later absorbed. By studying these details, astronomers reconstruct the family trees of galaxies, tracing which ancestors merged and when. It is a form of cosmic archaeology, digging through the debris of collisions to reconstruct the past. Every galaxy is not a single entity, but a community, assembled from many lineages, over billions of years. The role of collisions in shaping galaxies is not limited to their past. It also sets the stage for their futures. The rate at which galaxies collide, the environments where they are most common, and the outcomes of those mergers all shape the demographics of galaxies across cosmic time. Early in the universe, collisions were more frequent, galaxies smaller and more gas-rich, leading to bursts of star formation. Later, as galaxies grew larger and gas supplies dwindled, collisions became quieter, producing more ellipticals than new stars. The balance of spirals and ellipticals we see today is a direct result of how collisions have unfolded over the universe's history. In this way, collisions are not isolated curiosities, but the drivers of cosmic evolution. They determine how galaxies grow, how stars form, how elements spread, and how structures persist. They are the engines of change, ensuring that the universe is not static but dynamic, a place where the past is constantly rewritten into the present. To see a galaxy is to see a story, and to understand that story is to recognize the central role of collisions in shaping it. For us, the Milky Way is both a character in this drama and a witness to it. We live in a galaxy built from many past mergers, on a planet that formed from enriched material scattered by earlier collisions. Our sky carries the traces of this history, in faint streams and distant companions, being torn apart even now. And in the far future, our galaxy's next great collision with Andromeda will add another chapter, one that no human will see but that will shape the legacy of the stars we know. Collisions, then, are more than events. They are the way the universe writes its memory. The shapes of galaxies, the halos of stars, the scars in gas and dust are all texts waiting to be read. By studying them, we read the autobiography of the cosmos, a story written not in words but in light, gravity, and time. And at the heart of that story lies the simple, inescapable truth: galaxies are not eternal. They live, they change, and they carry forward the imprints of every encounter. Collisions are the script, and galaxies are the act. When we step back and look at collisions, not as isolated events, but as part of the universe's grand design, we begin to see their deeper significance. The cosmos is not static. It is not a frozen expanse of stars eternally shining in silence. It is alive with motion, interaction, and transformation. Galaxies collide because gravity wills it, because the invisible scaffolding of dark matter draws them together, because expansion is not uniform on small scale. Every collision is an expression of the same cosmic law: matter seeks matter, and in that seeking, new structures are born. To watch galaxies collide is to watch the universe breathe, exhaling chaos and inhaling order, over and over again. The universe has always been shaped by collision. In the earliest moments after the Big Bang, matter itself was clumping, colliding, and forming the seeds of galaxies.
Later, protogalaxies merged, building the larger spirals and ellipticals we see today. Even clusters of galaxies, the largest bound structures in the cosmos, are products of countless collisions. The architecture of the universe, the cosmic web, the filaments, the nodes, all comes from this ceaseless interplay of gravity and motion. When we talk about galactic collisions, we are not describing accidents, but the very mechanism of creation. Without them, the universe would be barren, featureless, and perhaps lifeless. And yet, collisions are also reminders of impermanence. The spiral galaxies we love to imagine, graceful arms stretching into space, dust lanes weaving like brushstrokes, are temporary. They exist for billions of years, but in cosmic terms they are fragile. Collisions erase them, scramble their order, and transform them into something else. Ellipticals, smooth and ancient, are the graveyards of spirals, repositories of stars that once belonged to elegant disks. The beauty we see in galaxies now is not forever. It is a moment in a cycle that ends with dissolution and silence. To grasp this is to accept that nothing in the universe endures unchanged, not even galaxies themselves. From a larger perspective, collisions are one way the universe balances creation and destruction. They tear apart galaxies, but in doing so they spark new waves of star formation. They feed black holes, which shine as quasars visible across billions of light years, but they also scatter the ingredients of life into interstellar space. They destroy order but create possibility. They are violent, yet without them, the universe would lack the richness we see. This duality, destruction feeding creation, is not incidental. It is the essence of cosmic evolution. Galaxies collide, and the result is not the end of a story but the continuation of one. The universe, however, does not allow this cycle to last forever. As dark energy drives expansion, collisions will become rarer. Distant galaxies will recede beyond our horizon, carried away faster than light can reach us. Only those bound to us by gravity will remain: the Milky Way, Andromeda, the Triangulum Galaxy, and the smaller dwarfs of the local group. In time, they will merge into a single, massive elliptical. Beyond that, the universe will seem empty. To observers living trillions of years in the future, collisions will no longer be visible. The grand story of galaxies meeting and transforming will have ended, at least in their corner of the cosmos. That future perspective highlights something profound about our moment. We live in a cosmic era uniquely suited to witnessing the universe's history. Galaxies are close enough and bright enough that we can see them colliding. We can trace their shapes, simulate their fates, and understand how their encounters shaped us. Billions of years from now, such knowledge will no longer be possible. The evidence will be gone, erased by expansion. The fact that we exist now, at the moment when the universe reveals its workings most clearly, may not be coincidence. Perhaps life and consciousness are more likely to emerge in an era when the cosmos can still be read. Perhaps our ability to understand collisions is itself a product of them. It is humbling to recognize that our galaxy is not special in this regard. All across the universe, other galaxies have collided, are colliding, and will collide. In each case, stars are flung into new orbits, gas ignites into new suns, and black holes stir in their core. If life exists elsewhere, it too may trace its origins back to these encounters. Civilizations may rise in galaxies, shaped by mergers, look up at skies transformed by approaching neighbors, and wonder what it means. We are not separate from this story, we are one expression of it. Our bodies, our world, our history are consequences of the same collisions we see across the sky. To see the universe in this way is to find meaning in its vastness. Collisions are not simply cosmic curiosities. They are the reason the universe is what it is. They are the reason galaxies grow, the reason stars shine, the reason elements exist, the reason life is possible. They remind us that change is not an exception, but a rule, that creation and destruction are inseparable, that beauty often arises from chaos. When we look at two galaxies on a collision course, we are seeing the universe at its most honest. It is showing us how it works, without apology, without permanence, but with a grandeur beyond comprehension. In the end, the fate of galaxies mirrors our own. We too are temporary. We too are products of collisions, cosmic, geological, biological. Our lives are brief compared to the timescales of galaxies, yet they are bound by the same laws of change. To contemplate galactic collisions is to glimpse our place in the cycle, to recognize that impermanence is universal, and that meaning arises not from escaping it, but from embracing it. We exist because galaxies collide. We wonder about them,
because collisions gave rise to the atoms in our brain. And when we imagine their futures, we are really imagining our own.
The universe is a story written in collisions. From the earliest moments, when clouds of gas clumped together to form the first galaxies, to the distant future, when the Milky Way and Andromeda will merge into one. The cosmos has never been still. Every galaxy we see is the product of countless encounters. Every star, every planet, every breath we take carries the imprint of galaxies meeting and transforming. Collisions are not the exception, they are the rhythm of creation. We tend to think of collisions as endings, as catastrophes that bring ruin. But on cosmic scales, endings and beginnings are the same. When two galaxies collide, their spirals unravel, their stars scatter, their gas ignites. But out of that chaos comes renewal. New stars are born, new worlds form, and the heavy elements that make life possible are spread across the universe. The very atoms in our bodies, the carbon in our cells, the oxygen in our lungs, the iron in our blood, all are the gifts of collisions long past. We are, in a profound sense, the children of galactic violence. And the story continues. In billions of years, our own galaxy will embrace Andromeda in a slow, graceful dance. Across the sky, an arc of stars will grow, until it stretches from horizon to horizon. Entire constellations will be torn apart and remade, familiar patterns vanishing, new ones appearing. To whatever eyes may be watching then, the night will be alive with change, a cosmic performance unfolding over generations. The Milky Way will be no more, and yet it will not be lost. It will live on, merged into something greater, a new galaxy carrying forward the history of both. But even this is not forever. Over trillions of years, stars will exhaust their fuel, galaxies will fade, black holes will dominate, and finally even they will evaporate. The universe will grow quiet, its collisions ended, its light gone, and yet in that silence will lie the memory of what was. The memory of galaxies spiraling together, of stars flaring to life, of planets forming, of life emerging, of consciousness awakening. The memory of a cosmos that for a time was alive with brilliance. We live now in a privileged moment, in a universe still lit by galaxies, still alive with collisions, still revealing its history to those who seek it. We can look out and see billions of galaxies, each one a chapter in the same story, each one carrying scars of encounters past. And in knowing this, we are connected to something far larger than ourselves. We are not apart from the universe. We are part of its unfolding, brief sparks of awareness, born from the very processes we seek to understand. So what happens when two galaxies collide? They create the universe, as we know it. They write its history, forge its elements, shape its structures, and give rise to the possibility of life and wonder. Collisions are not merely astronomical events. They are the pulse of creation, the reason there is something rather than nothing, the reason we are here to ask the question at all. And as we gaze into the night sky, at the faint smudge of Andromeda, or the arc of our own Milky Way, we are looking not just at galaxies, we are looking at the past, the present, and the future of the cosmos itself. We are looking at the story of everything. And in the quiet of that gaze, we can feel it. The grandeur of a universe that collides, that creates, that changes, that remembers. This is what happens when galaxies collide.